Hello, this is the review for your AP2 first exam on Thursday. I apologize for getting it done a little late, but everything's been on the way so my voice is finally returning. So what I do when I do these is basically I'm looking at the exam and sort of narrating through things that points of emphasis for you to be able to use. And basically the way the exam is structured, I'm going to give you the idea of how many. They're all either multiple choice, true, false. I don't even think there's a matching on it. Multiple choice, true, false. So I'm looking through this. Maybe all multiple choice. 60 questions. It's about 30 and 30. About 30 from the peripheral nerve special sense chapter 13, and about the same from the endocrine chapter. It's about how it's described. So we start with the peripheral nervous system, and the focus points are clearly eye and ear. I will tell you that. So you have to know all the different the 3 cranial nerves, 3, 4, and 6. That remember LR6, SO43. I have no problem with writing on tests. I don't, write that down. And this is what you should do. Assuming you can write on the test. This is the idea of why you write on the test. Is to put down, if you've memorized stuff, write them down now. Names of the cranial nerves, numbered 1 through 12, LR6, SO43, that kind of stuff. Significant numbers from nerve plexus, the layers of the eye, the 3 tunics of the eye, and what's involved in them. That's the kind of stuff you write down. If you're one of those people who's trying to cram it in, and I don't say that's the best way to do it, but we did that all the time. So sometimes, even on other kinds of tests or standardized tests, they will give you certain things. So in chemistry, you would typically be given like a periodic table and certain equations that you were going to use. Same for physics, and here, even though we don't necessarily do that unless there was something I needed to give it to you for, best way to do it is to get it right down as soon as you get your hands on the test. Stein's advice. First, understand, so the 3, 4, and 6, those are important. And I just mentioned the tunics. What's involved with the tunics? There are 3 of them. Remember, you have the fibers, which is the sclera and the cornea. Effectively, they're protective in nature. The cornea obviously facilitates, it's like a clear window for light and things that you see to come in through. The conjunctiva is not part of it. It's the choroid layer, or the vascular layer has the choroid that extends into that ciliary apparatus and ciliary ganglia. Effectively, it continues on to become the iris. The opening of the iris is certainly the pupil. Remember how 3, 4, particularly the 3rd cranial nerve, plays such an important role. The oculomotor nerve, and for distant vision when it's flat or flattened, and close vision when it becomes more rounded or oval, and the adjustments that are made into the sphincteric activity of the pupil. So people get smaller for close vision. The lens, being attached to the suspensory ligaments, becomes more rounded or oval or biconvex, and it allows for close vision to be refracted or sent to the appropriate area so you can see it, like the macular area, the fovea centralis. And the other is when if we're distant vision, our pupils are wide open so we get the big picture. And in doing so, the suspensory ligaments become much more taut, and they pull the lens flatter, and that's designed for distant vision. And the same thing, it alters the refraction. There's other apparatus that are part of the eye. Then you get the nervous layer, the retina layer, which is the nervosa layer. The rods and the cones are part of it. And they lead into those bipolar cells and then the ganglionic cells. There's a pigmented layer sort of between that and the vascular layer, which really where the light goes to. And those combination of pigmented material prevents scatter, which is really important. And we get that effect when somebody turns the lights on suddenly when in a very dark room, and effectively you're overwhelmed by it. The lacrimal apparatus plays a role with tearing. It kind of goes from superior-lateral, and the lacrimal duct and the lacrimal bone are much more medial and nasal and inferior. So you should remember all of those things. And again, the role of the suspensory ligaments, the shape of the lens, how they alter it. The lens divides the eye into segments. The segments are both anterior and posterior. The anterior is much smaller. That's the aqueous segment. Aqueous meaning it basically has water-based material in it. And the posterior segment, about 5/6 of the volume of the eye, of the material, sort of thing. The amount of material that's within that vitreous segment is very much jelly-like and different, but it's the main thing that gives the eye shape. The water-based segment or aqueous environment is significant because we're constantly making it and allowing it to drain out. But when there's a fault in that system, it either makes too much or it doesn't, or more often a blockage and drainage. That's when we get glaucoma, which can lead to blindness because of extensive pressure against the lens and really changing everything. So it's a big player. Don't forget all the different cells in again, rods, cones, ganglionic, bipolar cells. Cones, CO for cone, CO for color. They're all about light. It's like taking a good, even with a high-grade camera or high-grade, cell phone camera. If you want to get good color, you need to have the light that's there. And again, the interesting thing about the optic nerve is where it enters the eye, there are no rods and cones. It's the blind spot. Okay, and then as the nerve endings, so to speak, spread out from the nerve endings are sensory. So the signals incoming from the exterior, they all lead to that area we call the blind spot. So that's very significant. That's there. So you can call that the optic disc. You can call it the blind spot. Remember, the areas that have the most cones proportionally are the macula and the fovea centralis. That's the best area for color vision. And again, don't forget about the glaucoma. And we see cataracts are something that are opaque areas that are associated typically with aging, okay? But they're either typically in the lens or in the cornea itself. And really the name of them specifically is cataracts. That's what they are. They're opaque areas, clouded over areas. But what a cataract means is there is some area where effectively the light can't get through. And again, it's much more common with aging. Certainly smoking plays a role with it. Other disease entities all play a role with it. The light, as it enters the eye, and this is without getting into a lot of the optics and the details, in the visible light, effectively it bends 3 times when it goes through the cornea and twice when it goes through the lens. And that bending, basically, and the shape of the lens are able to focus the light depending on whether you're looking close looking at the computer screen or driving a car and looking far away. So what happens is if you have a concave opening, it tends to spread the light out, but convex tends to focus the light. When the light goes through it, if you go through it, it's just the way light is bent. And it's kind of a little bit, it's the analogy, I guess, would be oil immersion microscopy, that you're trying to change, going through one material like air, water, oil, glass, all of that stuff. But convexities are the way that we're able to focus that light on a specific point. And so the eye basically is designed to be, for distant vision, that is our pretty much of our default shape. And what happens is that effectively leads, because most of the stuff we do, unless we're, again, even if you're watching TV and the TV's at least 10, 15 feet away from you, you're still much more likely to be distant. Then again, if you're working on a computer, it's close, but typically distant, and it's designed for the pupils to be mostly dilated. And what do we do when you hear about someone's eyes accommodating? That's that tendency you probably all have done and seen that. Somebody will take a pencil and tell you, they're going to hold it in front of your face, and they're going to move it towards your nose and say, take a look at the eraser. Take a look at the pencil letters and tip. And your pupils will converge going towards the tip as it gets closer to your nose, and they will also constrict. That's called accommodation. Okay. We basically utilize different groups of pigments. There are 3 major pigments for color. There's only 1 for black and white. So the cones have 3 different pigments based on particularly each one of those pigments are depending on how the cones are designed to respond to 3 specific pigments in order to produce, the colors that are there. And on the other hand, rods just have 1. And typically the one which we associate with rods, it's all about, that's your night vision. shade and silhouette. Rods are 20 times more rods than cones, and the rods are much more at the periphery of the eye. So that's why you catch things out of the corner of your eye, particularly when you're driving at night or walking at night. How often did you can see a deer or something like that, and how often you don't see it when it's right in front of you, and all of a sudden you're driving the car, so you hit the brakes hard. Okay, those are the kinds of things, because you're just designed to pick up much more little subtle things, as opposed to color, which requires, a great deal of ambient light in order to be able to see adequately in color. So, and night blindness is related to the principal vitamin that produces most of the rhodopsin, basically the chemicals that change shape, and that's vitamin A, of course. So those are all things that are pretty much part of talking about the eye as much as anything else. Again, cones more central, rods more peripheral. Sense of smell. So this is where you have some of the roles of the cranial nerve. So olfactory is 1, optic is 2, 3, 4, and 6, oculomotor. And the numbers are fine. I typically will give you both of those. Typically, I do it by number. And 3, 4, and 6, again, oculomotor, trochlear, and abducens. That's the LR6, SO43. 5 is the trigeminal nerve. So just remember those. And so, and the similarities and the overlap between taste and smell, because they're chemical sensors, they have to be dissolved in some type of fluid, be it saliva or mucus, in order to trigger those particular sensors. We can, I think it's probably subject to change. So if you're just let me double check this to make sure I give you the correct information with regard to it. And, it depends on who you're listening to with regard to this thing. Let me take a look. And I apologize for the little delay. Realistically, and I've seen it differ, but most authors believe that we are sensitive to approximately 1 million different odors. The reality is that currently we're thinking that the number is significantly greater. For our purposes of the exam, go with 1 million. I think that's the best number that you can use for now. We underappreciated it, and then once we got to an age with more science and molecular biology, we're able to do it. So what happens with strong odors, and we're all familiar with whether it's a skunk, whether it's somebody throwing up, whether it's like my dog being indiscreet as he was this morning at Camp Bow Wow, on his way to enter, he's very excited. It's called olfactory adaptation. So what you're trying to do, your nose basically gets one of those smells and sort of says, okay, you got the smell. Now we're not going to let it overwhelm us. We're just going to adapt and not be constantly stimulated. And that's true for a lot of different senses. Hearing is not a whole lot different. We're able to adapt and make it a little bit less sensitive and that kind of a thing. Remember the major tastes for taste buds: sweet, sour, salty, and bitter. There are other ones like umami, and there's heat sensors are also for people like very hot, spicy food, and there's also fatty sensors. But the umami is one that's a lot, particularly in the cooking realm, because it's related to certain amino acids, particularly glutamates, and that's the old story with MSG that used to be used as a powder extensively in Asian cuisine. And a lot of people have problems with that because it's somewhat of a stimulatory neurotransmitter. So, and there's probably a fair amount, and again, I want to double check to make sure I give you the right number about this, is the amount of overlap between smell and taste. And there's different authors. They're very much closely linked. I would say, and I think it's pretty consistently found, that about 80%, okay, I think it's the best number to go with. Smell is about 80% of taste. And this is one of the things that happened a lot to people with COVID or similar problems, that they couldn't taste anything, they couldn't smell anything. It's probably more had to do with smell than it had to do with taste. But the fact that the smell sensors were affected in that because it starts mostly as upper respiratory, probably played a more significant role. Auditory stimuli are certainly mechanical stimuli. They're physical changes, particularly in the eardrum. Okay, remember the two names of the two muscles, the stapedius and the tensor tympani. They're the ones that adjust the tension on those three little bones, the incus, malleus, and stapes. And what they do is that's part of your auditory adaptation for certain sounds. And again, the cochlea is for hearing. The semicircular canals are for balance that are there. The hair cells are embedded in the ear for hearing, what's called a tectorial membrane in the cochlea. They sit on the basilar membrane. The basilar membrane is what moves with sound, and the hair is being embedded in the membrane above it, so to speak. And when they move back and forth, and you get either bending in one direction or the other, that's really the trigger for all that potassium, calcium-related movement that basically triggers sound. So the auditory cells move, okay, with the basilar membrane, even though the hair cells themselves are embedded in the tectorial membrane. Prolonged exposure to 90 dBs or more over time is what does people in the hearing. There's the old saga with rock concerts, particularly with the musicians who stood in front of those giant amplifiers. And I will tell you from personally that they were really loud. I mean, I do not have. It depends on where you're located. We went to a number of relatively smaller venues that were pretty darn loud. And none of the musicians were wearing anything like they do today. I mean, you go to a studio today, you will have headphones on. It's a very controlled environment because there are so many problems associated with it, particularly because we didn't know any better. And I think that's basically the first half of the test. Well, test section number 2 has to do with the endocrine system. So what are they? They're hormones that are released directly into the bloodstream. Okay, they're ductless. Sometimes they're proteins, but not always. Okay, because fats, cholesterol-based hormones, as well as protein hormones, how they, even though the glands are relatively small, the defining factor is they travel, for all intents and purposes, by way of the bloodstream to different target organs, whether they're very close or far away. So we classify them as either protein, or rather even peptide based, which would be made of amino acids. Typically, it could be as little as 2 with thyroid hormone, or even something very, very large like insulin. And then the ones that are steroidal based, and the steroidal based ones will have the same base ingredient, and that is cholesterol. Effectively, what we do is we lop off. Cholesterol has roughly 27 carbons, but it has 4 carbon rings. And you can find the structure anywhere. Not that you have to know it, but we kind of lop off the extensions on those that are sort of protruding from some of those carbon rings, and then basically the body adds stuff to it. So whether we were making it in the laboratory or we were making it inside our bodies, effectively you start with the quote-unquote cholesterol nucleus, which is those 4 attached ring structures that are there. So that's important. With the exception of thyroid hormone, which remember is a symmetrical 2 amino acids with iodine, and because of the symmetry of it, it effectively is it's fat soluble because it effectively becomes nonpolar, because it's not always about being made of fat. Symmetry plays such a vital role in that, from chemical speaking. All the other, so the thyroid hormone and the cholesterol-based or fat-soluble hormones are by definition fat-soluble. So all of those are in one category. Everything else is water-soluble. Okay, and so where the fat-soluble ones can pass through the membrane of the cell, they interact with receptors within the cytoplasm. They can pass through the nuclear membrane and directly affect transcription and translation. The water-soluble ones all have to work through second messenger systems. So they don't work directly. They work indirectly. They attach on the outside. They don't go on the inside. They set up that chain reaction. Remember those G protein related pathways, and effectively work like with insulin, tyrosine kinase. And typically they use things like The second messenger, the first messenger, let's say, is the insulin. The second messenger are things like calcium ions or something called cyclic AMP, which is broken down ATP. Like that. So that's also part of the situation. And so again, the lipid soluble ones is transcription and translation. The water soluble ones are the second messenger system, and G protein receptors. So those are all part of it. And again, calcium and cyclic AMP are the principal second messengers we see in most of those. And so there are different things that can affect it. For instance, fight or flight is a neural stimulus. Okay, a near-death experience, very scary experience will trigger fight or flight. Effectively, that is a way that neural stimuli can overwhelm the system. The endocrine system is such an intrinsic part. When you think of chemical controls, we look at what are called humoral controls, things that are in the humor or the blood, like calcium levels and parathyroid hormone. And then others are hormonal levels. So estrogen and progesterone or testosterone, as long as they're in adequate amounts, the pituitary doesn't make more follicle stimulating hormone or luteinizing hormone. So those are all part of it. The posterior portion of the pituitary, which is really part of the hypothalamus and has that stalk called the infundibulum, the two classic hormones that it releases, okay, are antidiuretic hormone or vasopressin and oxytocin. But they also generate both releasing hormones, RHs and IHs. So, and effectively, the RHs, releasing hormones, induce the pituitary to make a short trip to the anterior pituitary to release something, let's say GnRH for gonadotropin releasing hormone. So that'll induce the follicle stimulating and the luteinizing hormone, or they have inhibitory hormones like GHIH, okay, growth hormone, inhibitory hormone. So it will slow down the amount of growth hormone if it's not called for. So in general, if anything, probably numerically, the hypothalamus makes more hormones because of those releasing and inhibiting hormones, in addition to the antidiuretic hormone, which works directly on retaining water, and oxytocin, which works almost exclusively, though it does play a role in lactation, on birth canal contractions vis-a-vis vaginal delivery. So antidiuretic hormone, again, will increase the retention of water, okay? So there'll be less water in the urine, making less urine. Antidiuretic, when you diurese, you're making urine. So, I mean, it's the opposite of, so we talked a little bit, and we'll get back to it more with the heart, with ANP, atrial natriuretic hormone, and that means it induces sodium to be released into the urine and water follows it, so it's opposite each other. Okay. So all of those are important. So you must know what I call the big six. What's made by the anterior pituitary? Human growth hormone, thyroid stimulating hormone, adrenocorticotropic hormone known as ACTH, thyroid stimulating is TSH, HGH is human growth hormone. Okay, the others are all reproductively based. FSH, follicle stimulating, LH, luteinizing hormone, and the one that we is other than playing a role in lactation, is the oddball, prolactin. The widest range of the target cells is surely human growth hormone, because that affects nearly all of our cells. Thyroid stimulating is the thyroid, luteinizing and follicle stimulating, ovaries, testes. Prolactin, for the time being, let's just think of lactation in an isolated area. No, it's not necessarily all it does. ACTH is the adrenal cortex, so it's different. Okay, so understand estrogen and progesterone, they are luteinizing hormone as well as testosterone. Luteinizing hormone makes the reproductive hormones we're so familiar with, where follicles make eggs and sperm. So the follicle stimulating hormone is eggs and sperm. Okay. Antidiuretic hormone, and it's rare, but it does it because if you're not making enough of it, you're losing water. If you're losing water, you're thirsty. So it's a kind of diabetes known as diabetes insipidus, or salt diabetes, because the urine is more salty than it should be, versus diabetes mellitus, MELLITUS, has to do with typically insulin deficiency or insulin lack of activity or problems with the receptors. We'll deal with that in a second. And that is sugar diabetes, because you didn't have extra sugar in the urine. Remember the important role of iodine in the structuring of the active thyroid hormones T3 and T4. Basically, all the T4 gets converted to T3 because T3 is really the active form, even though both of them are produced by the thyroid. And thyroid hormone is another one of these. Remember, it's not a pituitary hormone coming from the thyroid, but if, just like human growth hormone from the pituitary, it affects nearly all cells. Because the thyroid just kind of keeps everything in balance, going at the appropriate rate or the amount. In the adrenal cortex, you have 3 levels going from external to internal, these 3 zones. And you don't have to know the names of the zones, like the glomerulosa and the reticulum, all that stuff. But the outermost zone is aldosterone. And aldosterone is immensely important for blood pressure. Surely the most important factor in keeping blood pressure regulated through a number of mechanisms, that renin, angiotensin, aldosterone mechanism, where we're going to touch on several times in this class. The aldosterone, the big deal with that is it inserts little tubules in the kidneys that pull back sodium out of the urine and back into the bloodstream. And again, where sodium goes, there you go again, water is sure to follow. So it increases sodium retention by the kidney and therefore increases water, which means increased volume in the bloodstream, and that means increasing blood pressure. So the big pathway again is the kidney produces something called renin. Okay. Renin is triggered when the blood pressure by the sensors in the kidneys, or the chemical constituent of the filtrate in the kidneys, is not where it's supposed to be. And if that's the case, it produces this chemical called renin. Renin then basically activates a circulating chemical in your bloodstream called angiotensinogen. And basically, what it does is it makes it into something called angiotensin type 1. That angiotensin type 1 in the lung is converted to something called angiotensin 2, and that's what basically triggers the aldosterone. Angiotensin is extremely powerful, has 4 different activities. We'll touch on it throughout the course. I'll mention to it now. Its name tells you it's one of its main activities, tensing angio, which is blood vessels. It makes them more taut. It squeezes them. That increases your blood pressure because now the fluid is under greater pressure. It makes you more thirsty, so you bring back fluid. Okay. It increases the release of an antidiuretic hormone that holds in more fluid. And most importantly, it triggers the release of aldosterone. The adrenal cortex is the only area in that most internal zone where women make testosterone-like substances called androgens. Men obviously make it from the testes as well as from that area. So that's where we see, that's the only place in that part of the adrenal cortex. Remember, the islet cells in the pancreas are alphas and betas. They make both insulin and glucagon. Okay? Glucagon acts on the liver to increase the amount of blood sugar. It's basically the balancing out between insulin, taking blood sugar out of the bloodstream into your cells to utilize for energy, and the glucagon trying to make it not such an extreme reaction. So they kind of work in concert. If you're just had a candy bar, you're going to have a lot more insulin. But your body's also going to release a tiny amount of that glucagon to sort of make sure that your sugar doesn't go up precipitously. When you can't do that, that's an indication that diabetes could be in your future. It's called being pre-diabetic. Insulin acts on nearly all cells, and by bringing the sugar into the cell, it lowers your blood sugar. If it's not in the blood, then the blood sugar gets lower. The fact that you bring it, it's still in you, but now it's going to be utilized for energy transformation. Type 1 diabetes and type 2 diabetes. Type 1 has to do, if you wanted to state it very, very simply, insulin production. Insufficient. Either fails completely or you're making a trace amount. It doesn't. Type 1 by definition is not about the receptors. It's not necessarily about diet, though those may be indirect causes that are there. Okay. Type 2 diabetes is much more of a problem specifically with the receptors. Either the receptors are non-functional or there's some alteration in the receptor that's producing some unusual response. And again, when you talk about diabetes mellitus, or known as sugar diabetes, classically, it means there's high levels of blood glucose, frequent urination. There's other things that go along with it. So we do see that's the three polys. Polydipsia, thirsty, because diabetes is the great thirst. Polyphagia, you're hungry. Your cells, all your cells know is they're starved for energy. Okay. Polyuria, because the glucose is what we call an osmotic diuretic. It's pulling water along, so you're diuresing more. And because you're not doing energy production, fatigue is part of it as well. The big problem with long-term diabetes, be it type 1 or type 2, is you end up having to utilize fats excessively. And the trouble with fats is, as an energy source, unless we rid ourselves of them, and typically diabetics have kidney problems, so it's harder to rid themselves of this by way of the urine. That's why the keto diets and things like that work so well, because you have to hydrate a great deal and flush these systems, and use healthy fats rather than bad fats. And without getting into the chemistry of it, effectively what those fats do is they form what are called ketone bodies or keto acids. Okay, fat, two carbon units of fat slam into each other, make these ketone bodies or trans fatty acids, and they're very damaging to blood vessels. Okay. And so again, the fatigue is very much because you're just not generating enough energy. Erythropoietin is the big chemical in the kidney. Okay. Leptin is the one that you hear about from fat cells. That's another hormone that's there. Okay. And again, that atrial natriuretic peptide is something that happens when you have too much blood pressure. And it's pushing the atria, those chambers in your heart, and their ability to release this interesting peptide protein called atrial, because it's from there. Natriuretic, natri means sodium, uretic means to get rid of it in the urine, and peptide, or AMP, and then basically it acts opposite aldosterone. It's causing more sodium to be excreted, and water follows it. And certainly, then lastly, the thymus is important because it plays such a pivotal role. We'll get to it in immunology and the development of white blood cells, specifically T cells, which is where they get their names. Killer T cells and helper T cells, all of those kinds of cells that we'll get to in immunology are activated by what are called thymosins, hormones from the thymus. Even though the thymus isn't very impressive in size in an adult, it's very impressive in what it does. And that's everything. So that concludes this little presentation. And I will send it to you and let you know that it's there. And thank you very much.